All right, algebra class. Haven't done a lot of these videos this semester, but I know that with us reviewing a previous unit, this is the perfect time for me to post this video. All of the content that we are reviewing right now, we have already taught and assessed over on a previous unit. So I'm going to go through this fairly quickly, but I wanted to create this video so that over the weekend, as you're solving the homework questions on Delta Math, you could refer back to it at any time that you wanted, okay? First, we'll start off with just simplifying radicals that are all perfect squares. Okay, and so the whole point here anyways is if we have a perfect square, the square root of that perfect square becomes a rational whole number. Okay, meaning if you started with a number like x and squared it and then square rooted it, you'd be back to the number that you started with, x. So for example, if you started with a number 6 and you squared it, you would get 36. And then if you were to square root that 36, you would be back to 6. Okay? Same thing here. You can think of the square root of 100 as, hey, I started with 10, squared it, got to 100. Now we're square rooting it to get back to 10. Okay? These other two examples, square root of 144 is 12, square root of 64 is 8. So this is like phase one of simplifying radicals is, well, what happens if it's a perfect square already? Well, that's easy. We just remove the square root symbol and we square root the value and get the numeric value that was the actual square root. Okay. Next type of problem that we're going to be simplifying is when it's not a perfect square, but it has a perfect square factor. All we're looking for in each of these examples is a perfect square factor. So for example, 20 has a bunch of factors, okay? But we don't need all of these factors. In fact, 1 and 20 don't help us because that does not make this any simpler. And if we were to use 2 and 10, that would not help us either because 2 is not a perfect square and neither is 10. However, if we use 4 and 5 as our factors, and we break root 20 up into root 4 and root 5, the reason that that becomes a really successful next step is that it directly leads to our final answer because we're using a perfect square factor, which, like we just showed you on the previous page, if you have a perfect square and you square root it, we remove the radical symbol. So that's what happens here. We have a perfect square of 4. We're square rooting it. So that removes the radical symbol and it just becomes a regular 2 times the square root of 5 for a final answer. Okay? So next couple steps. Root 8 becomes root 4 and root 2, thus giving us a perfect square, which then allows us to reduce it to 2 root 2, okay? Again, root 24 also uses the perfect square root of 4, and so the factors would be root 4 and root 6, which then becomes 2 root 6, okay? Now, I want to purposely, on this next question, take the longer route in simplifying it so that you see what happens just in case you don't take the largest perfect square factor out at first. So we have kind of like a process for doing this, and it's most beneficial for you when you're simplifying something like root 48 if you go ahead and try to factor out the largest perfect square factor first, which if we were to write all of the factors of 48, 1, 2, 3, 4, not 5, 6, 6 would multiply to 8, 4 multiplies to 12, 3 times 16, 2 times 24, and then 1 times 48. So these are all the factors that go into 48, okay? So these are all the different concepts or numeric values that we could have factored this into, and obviously each one comes with its own pairing. For example, 6 and 8, 4 and 12, 16 and 3, 24 and 2, and so on and so forth, okay? But I want to start crossing off numbers that we don't need. First off, using 1 and 48 never helps us because it doesn't make this any different, okay? Second off, let's cross off everything that's not a perfect square. 2, 3, 6, 8, 12, 24. So notice there's two perfect squares here. I would at this point suggest you use the larger one always, because ultimately we're trying to factor out as much from this radical as possible. So the bigger the perfect square, the bigger the concept is that we're removing from the radical symbol. All right, but just in case you didn't recognize that from the beginning and you got on this train of pulling out a root 4, okay, let's show you how you would have done this problem had you chosen to partner root 4 up as the perfect square factor with the other factor that would multiply to give us 48, okay? Then you would end up with 2 root 12, and you'd have to keep going because root 12 has its own perfect square factor. Root 12 can be represented by root 4 and root 3. Notice I brought this regular 2 down, so it's really 2 times root 4 times root 3. Which becomes 2 times reduce root 4 to regular 2, because that's what it simplifies to become, times root 3, and we get the final answer of 4 root 3. Okay? So that's one way that we can solve it, and I wanted to show all of the process there, just in case we don't pull out the largest perfect square factor at first, which is totally okay. I just wanted to make sure we knew how to do this. Okay? However, you would have gotten the same answer of 4 root 3, it just would have been a lot quicker to get there had you factored out the largest perfect square factor at first. Had we chosen root 16 and root 3 as our combination, you would have seen this was a much easier problem. It was basically a one-step problem because then root 16 becomes 4 and root 3 just stays as root 3. So notice we get the same answer. Okay? But I just wanted to show you guys how to do that per se. Okay, so the next skill, actually, I already kind of previewed it for you, which is what happens when there's a numeric coefficient out front, okay? Well, when we have a numeric coefficient out front, we're literally just multiplying that to whatever the root 18 simplified to become. Root 18 becomes root 9 and root 2 when you break it up into its perfect square factor parent. Remember, we don't need both factors to be perfect squares. It's okay for root 2 not to be a perfect square. In fact, if they were both perfect squares, that means this number is already a perfect square. Okay? So this becomes 3 times, root 9 is actually now going to be regular 3, and then the root 2 stays. So this gives us a final answer of 9 root 2. Okay? I'm going to press pause now on my video, and you guys can go ahead and solve, or sorry, not solve, simplify negative 2 root 27. Okay, and we're back. So negative 2 root 27, we're going to first need to split root 27 up into its perfect square factorization, root 9 and root 3. Okay? Root 9, we just said, was regular 3. We keep the root 3 here. And that gives us, when we multiply our outside values, negative 2 times 3 is negative 6, root 3, final answer. Okay? All right, so let's look at a couple situations when we're simplifying radicals across a fraction bar. Now, step 1, level of difficulty is what happens if they're both perfect squares. This is like separating this into root 49 over root 36. That is a property we're allowed to use in simplifying radicals. The radical of a fraction is the same thing as the radical of the numerator of our fraction divided by the radical of our denominator of our fraction. And since both of them are perfect squares, we can reduce this to 7 over 6. Okay? Another example right here would be 4 over 8, but then that needs to be simplified to 1/2. Okay? There's a second way that we could have done this problem, because when you notice that we have a radical across a fraction bar, if both numbers have a common factor, we can divide that common factor out. Notice they both have a common factor of 16. So we also could have turned this into 1 over 4 inside our radical, because that was just simplifying our common factors on top and bottom of our fraction. So just like we would naturally reduce a fraction, we can reduce the fraction first, then separate the radicals to be on top and bottom, and then take the square root of the top and bottom, okay? Which I personally like that method as well. Here's a scenario where our numerator, when we separate it, it is no longer a perfect square, but our denominator is, which is fine. That just means we now have to go ahead and simplify our numerator into root 4 and root 7, because that still is how you create root 28. But this gives us now a perfect square factor, which means when we take the square root of that perfect square, then it becomes 2 root 7 over 5. The only other thing we're going to look to do is see if 2 over 5 can reduce. But since 2 over 5 cannot reduce, there's nothing to be done here. Same exact properties can be applied here, where we can split this into root 20 on top. Now regular 4 on bottom, because we took the square root of 16. Root 20, I'm just going to quick hand through this. This becomes 2 root 5, because this would have been root 4 and root 5. Now I want to highlight the fact that we've got a 2 on top and a 4 on bottom. Now we have two numbers outside the radical which have a common factor and thus can be reduced. So we would reduce that to 1 over 2, and we don't actually need to put the coefficient, we don't need to put the numeric scalar out front of 1. We don't need to do that. Okay? Whoa. We can literally just leave it as root 5 over 2. Okay? Quick little reminder. I'll let you guys press pause and take notes on this now. And you can unpause, and hopefully we can be back at it. So notice here, perfect square, and we have an even degree. So this just becomes 2 on the outside because the square root of 4 is 2. And then we take half of that exponent. Because in essence, the square root is like multiplying our exponent by 1/2. Okay? Over here, we have 4 that comes out front. M cubed can really be thought of as m squared times m. Sorry, that's not, I don't think I always write m's the same way all of you guys do. So, boom. There we go. Okay, because m cubed is really m squared times m, because that's 3 of them still. Those are inside the radical, because they're inside the radical clearly. These two come out, and we just said it's like taking half of that degree. So now it's just a power of 1 on the outside, and then we had the 1m left over on the inside. Okay? We show that right there. Oopsies. I guess I never filled these out. X root x, x squared, and so on and so forth. Okay? We've already done this unit though, so this should all be memory by now. Okay? Over here, this root 9 becomes regular 3 on the outside. Root a to the 5th is the same thing as a to the, sorry about that, it's the same thing as a to the 4th times a. Again, we have an even degree now, so cut that in half and leave the extra a in the radical at the end. Simplifying this, because 2 times 3 does need to be done, we have 6a squared root a. All right, so hopefully this is starting to refresh your memory from this unit that we did. Okay, right now just remember root 8, that's 2 root 2. Again, we had a full unit on it, plus we've done root 8 earlier in this video simplifying it. So now we've got negative 3 times 2 on the outside. Okay, we do have this root 2 on the inside still. Y to the third, we already said that's like pulling one y out, leaving one in, because this 1 on the outside was really 2 on the inside, if you guys recall. All right, 1 on the outside is like 2 on the inside. Okay. Let's just do this top one right quick. 2 times m, I pulled the m out right away, times root 25 and root 2. Okay, because that's what root 50 is. Root 25 becomes regular 5. Multiply to this 2, 10m root 2. Okay? Pretty straightforward. All right. Let's go through. I think most of these should be pretty simple. Root x squared, that's just x. Take half of that degree, now it's a cubed, right? C to the 9th is really like saying c to the 8th times c. That's 1 more than 8. Half of those 8 become 4 on the outside, and the leftover c on the inside. And this is the money round question that I wanted to make sure that we went over. Okay? This will kind of be our last example for the day. I'm going to press pause now when I'm showing this video to you guys, and you guys can, or pause at home. I want you to try to work your way through this, and then we'll kind of regroup once you're done with it. Okay, you should be back at this time, so I'm going to kind of highlight through how I would go about doing this. Root 12 becomes 2 root 3. This is an even degree, so it really becomes a to the 4th on the outside. Sorry, yeah, a to the 4th on the outside. This is an odd degree, so that's really like saying b to the 4th times b, which becomes b squared on the outside times root b. And I think highlighting through these colors, hopefully we see this negative 3 needs to multiply by this 2, so we've got negative 6. This a needs to combine with these 4 a's to make 5 a's. Okay? This b squared is here. We still have this 3, and we still have this b. Hopefully color coordination has assisted. Listen, this has been a quick little recap and review of simplifying radicals. I hope that this video does end up helping you guys, okay? Watch it anytime this weekend to help with the homework. Take care.